Yes, Loic.
Just like a general question. For all the formulas, you have like the summation as from n equals 1 to infinity. Does it always have to be n equals 1, or can it also be n equals 0 or n equals something else?
It can be n equal anything.
Okay.
Yep. Any other questions? All right. Well, that was exciting. We're going to take our reality check, so I'm going to go ahead and pause this 30 seconds. Hey. Any questions about number 1? Hopefully that didn't take too much time. Once you figured out. Oh, wait, geometric. Anybody, one more time looking? Ready? Here we go. Here's no, oh wait. There's number 2. Any questions about number 2? Anyone? Bueller? Can't do that voice. You know the actor that does that, teacher, and Ferris Bueller's Day Off is actually an economist. He's also an actor now, but yeah. I know, right? The guy that played Sir Davos in Game of Thrones used to be an electrician.
Really?
Yeah. A little trivia there. Anybody need more time looking at this one? Then number 3 is...
That's D.
That's D? Ah, crap.
I say we just take the point off. Yeah.
No.
No, we just take it off.
Why would that switch?
I was really hoping it'd be ace. That's what I was going for, right? Apparently. Yeah. All right. Now it's act. Anyway, did you guys play your Wordle today?
Yeah.
All right.
That was hard. I was so mad.
Yeah. It's always horrible when there's like somebody new playing and they don't know that it's the same word for everybody and they spill the beans. You're like, no! Anyway, the word was not ace, in case you're curious. Yeah. But that's why, Wordmaster, you can always do Wordmaster. Actually, I did read if you download the web page right now, then it'll, like, I guess there's like a couple of years worth of puzzles in there. So you're set for a couple of years. So everybody download the webpage right now and save it. All right. Yeah, let's start the new lesson. Why not, right? Here we go. We're doing section 10.3. Convergence of series with positive terms. And I'm just warning you, today is going to be chock full of stuff. There's going to be some times, though, where I might recommend, it's not necessary that you write this down. But most of it we're going to write down. There's going to be a lot. Just warning ya. Basically, we're going to spend 2 days on this section. It's kind of a meaty section. But what we're going to do today is just get through all the material in the section. But I'm going to give you a lot of different tests for convergence today. And then tonight's homework will obviously be using these tests, but it'll tell you which test to use. And then next class, so the payoff for doing a lot of notes this time is there's not going to be a lot of notes next time. Next time, there's going to be a lot more time for you to do your homework, but next time the big focus is, now we have all these tests, how do you choose which one to use? And then your homework will be, use any method. So we're going to, I've debated in previous years, like splitting this up into the material into 2 days, and I find it's better. Let's just get it all over with now, and then we have a couple of days to kind of noodle on it. So anyway, with all that said, the first thing we're going to do is the dichotomy for a positive series. I know, right? Who comes up with these words? Dichotomy for positive series. dichotomy. And, I mean, it's a simple thing, but it's actually an important thing that we talk about. So it is this. If S equals the summation of A sub n as n goes from 1 to infinity. So basically an infinite series. And if S is a positive series, then number 1, the partial sums S sub n are bounded and S converges. So what does that mean? Well, when we say that the partial sums are bounded, so remember the first partial sum, S sub 1, would be the sum of the first term. And then S sub 2 is the sum of the first 2 terms. S sub 3 is the sum of the first 3 terms. And so on. So if we keep listing all of the partial sums, they will never go above a certain value. That means they're bounded. They're bounded by whatever that value is that they never go above. And if that's true, that's basically the definition of convergence. So we say that it converges. So either that's true, or the partial sums S sub n are unbounded, and S diverges. The series converges or diverges. It can't be a maybe, sometimes converges and sometimes diverges. None of that. No wishy-washy here. It's going to do one or the other. And there's the dichotomy. The dichotomy basically means all the possible cases are one of two things. So, now that we've established that, all of our positive series that we are going to talk about today will either converge or diverge. So now let us talk about some ways that they do.
So the second one, bounded A as diverges, or is it and S?
And S, yeah. Can I squeeze it in there? And S diverges. And. All right, our first test for the day. The integral test. I bet you can't guess what this involves doing. Differentiation, exactly. Yep. No, sillies. It's integration. Okay, the integral test. Let's go blue. So, consider this. Consider this if you dare. The summation of A sub n as n goes from 1 to infinity, and let f of n equal A sub n. Remember, A sub n is just a list of numbers, so it's not a continuous function, it's a discrete function. If we were to plot the sequence, it would just be distinct points. So we're going to make a function out of this that can then be a continuous function. So if f of n, the function, is positive, decreasing, and continuous. So those are going to be the necessary conditions to meet before you can apply the integral test. So as long as those three conditions are met, then the integral test applies. So what is the integral test? Oh, yes, Karen.
I have a question about if f is continuous. Because we're forming it out of a bunch of points, how do we know whether or not it's continuous if it's just, like, if we're the ones making the function, why can't we say it's continuous?
Well, the function is based on whatever is here.
Okay, so if at any point n is not a function value,
I'm going to wait and fully answer that, I think, with the example. I might answer it with the explanation of why the integral test works, but if not, the example will definitely explain it. Oh, okay. So, number 1. If the integral from 1 to infinity of f of x dx converges, the series converges. And, or maybe I'll say or, if the integral from 1 to infinity of f of x dx diverges, the series diverges. Ba-dum-bum. Bloop, 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 bloop. So, let's look at why this works. This is an easy one to just kind of look at a picture. So, just going to give myself a little more room. I'm going to imagine a graph, but we really only care about quadrant 1. And the reason why we only care about quadrant 1, my input values, actually I'll go back here for a sec. My input values are going to be n going from 1 to infinity, so my input values are positive. And I'm saying that this is a positive series, so the outputs are also positive. All the action's going to happen in quadrant 1. And so if the function is positive, decreasing, and continuous, the key right now is the positive decreasing part. That means each term in the series is positive and they decrease. So I'll go ahead and make that 1, 2, 3, 4, and so on and so on. And let's just say that a sub 1 is up here, a sub 2 is here, a sub 3 is here, maybe a sub 4 makes, it looks really straight. I was trying to make a bigger jump. How about makes a smaller jump? But it's always decreasing. Now, imagine then that this point is up, at a sub 1, this is at a sub 2, this is at a sub 3, this is at a sub 4. And then we have the function that we create from these that would basically go through all the points. So we'll say that this is y equals f of x. Now, because the width of each one of these intervals is 1, I can basically imagine rectangles under this curve. And because this curve is always positive and decreasing, these rectangles are always going to be below the curve. And so if the area under this curve converges, which is basically what this definite integral says, then of course the sum of these rectangles would also have to converge, and the sum of these rectangles represent the value of the series. And so that's why the integral test works. Yes?
okay, so if the function is decreasing and continuous and it goes from 1 to infinity, how can it ever diverge?
Well, wait, did you say the series or the integral?
The function.
Okay. Well, we're saying, though, that this integral doesn't represent just the function, it's the area under the function. So this is an infinite area because the function is infinite, or the limit is infinite. So sometimes the value of that infinite area converges and sometimes it doesn't.
Okay.
Does that make sense?
Not really. Then okay. So if the area converges down to a value that value would, it say it's 1 over x, right? That value would still theoretically be infinite.
No. And actually 1 over x diverges. So let's not look at that one. But but let's look at oh wait, I already have that. Let's look at y equals 1/2 to the power of x. So let's say that this is 1/2. So when x is 1, you're up at 1/2. Then you go down halfway, then you go down halfway, then you go down halfway, and you keep doing this. Now, it's always going to stay positive, but as long as that function, as long as my upper limit is infinity, the area is infinite, but it does converge to a value. Because we know that the summation of 1/2 to the x is 1. The area actually under that curve is 1. Crazy. Actually, it may not be 1, but it will be. It will converge. We know that. Remember when we did improper integrals?
Yes.
This is basically improper integrals. And we saw sometimes improper integrals converge to a value. Sometimes they don't. And so it's crazy. Because even though we're talking about adding numbers forever and ever and ever, sometimes it converges to an actual value.
Okay.
Like the 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, yada, yada, yada. Same kind of thing.
Okay, last question then would be, is the area under the curve always equal to the converging point for the summation? Because you're saying that for 1/2 it does equal or doesn't.
Well, actually, I'd have to work that out. That might have been wrong on that. But,
like it doesn't say that the integral is equal to the center.
right. We're just saying that if this area converges, it's going to force the sum of these terms to converge because the sum always has to be less than the area. Any other questions on that? Let's see how this works then. Let's apply it and see what does the work look like that you have to do. So let's look at this guy right here. Determine the convergence. I don't know if you can read that. Determine the convergence of the summation of 1 over 3 to the power of natural log of n. So, now don't worry tonight, because one of the big questions is probably going to be, especially after we learn all the different tests we're going to learn today, how do you know when to apply which one? That's not the focus for today. We just want to get our feet solid on how to use these things, and that's the next class. Next class we'll look at how can you tell which one to use, and you don't always know, and we'll see that today. Anyway, but we are going to use the integral test. This can be our example for the integral test. So what I'm going to do, though, is I first want to define my f of x. So my f of x is just going to be the argument to that summation. 1 over 3 to the natural log of x. Now, it's okay to just look at that and go, will that ever be a negative value? What do you think? Can that expression 1 over 3 to the power of natural log x, can that ever be negative? Okay, that's good enough. We just need to state that it's positive. Now, as far as decreasing goes, just look at the directions. If the directions say you don't have to prove the conditions are met, just state that they're met, then we can just say that's decreasing. But let's think about that. Is that going to be a decreasing function? Yeah. Because as x, and now we're going to assume, and you're going to see I'm going to write this down, because x is taking the place of n, and because n is starting at 1, we're going to assume that x is greater than or equal to 1. So if x is greater than or equal to 1, the natural log of x is going to increase, which makes 3 to that power increase, which makes the fraction decrease. So it does make sense. But, if we didn't know if we could use the integral test, you got to ask yourself that. Is that a decreasing function? It is. What if we had to actually prove it's decreasing? How could we prove it? A little calculus, maybe? Yeah, take the derivative and show the derivative is always negative. So let's just see it. Let's just do it so we remember. So if that's f of x, f prime of x. I'm going to just rewrite f of x as 3 to the negative natural log x. How do we take the derivative of that? Do you remember? Sid. That is exactly right. So the formula for the derivative of a to the u, natural log a, u prime, in whatever order you want. Is that always negative? Yeah. As long as x is greater than or equal to 1. If x is greater than or equal to 1, I mean natural log 3, obviously, that's positive. 3 to any power, positive. And if x is itself positive, this fraction will be negative. So yeah, this will always be negative when x is greater than or equal to 1. So, and then the other thing is x is greater than or equal to 1, is there any place where this is going to be discontinuous? Okay, so we're good. So now we just have to state these things. That f of x is positive, decreasing, and continuous. So the integral test applies. Now we just got to use it. So any questions so far? So now we evaluate this integral. This improper integral. And it's improper. So, oh, yes. So, because the way we're defining f of x, x is in the same place that n was in the series, and because n is going to be greater than or equal to 1, we can assume that x is greater than or equal to 1. Yeah. And actually, on that note, well, I'll talk about that in a second. Okay, so it's an improper integral, so we're going to turn this into a limit problem. I'll just use a. The limit as a approaches infinity of the integral from 1 to a of 1 over 3 to the natural log x dx. Now, there's actually a sneaky trick to finding the antiderivative. Anybody have an idea before I give away what the sneaky trick is? Sneaky trick. All right, here's a sneaky trick. If I start, I'm just going to look at the denominator, 3 to the natural log of x. If I start with that, I can rewrite the 3. I can make that say e to the natural log of 3. So that's the same thing as 3, but that's still to the power of natural log x. And is that okay? And then I can say that that's equal to e to the natural log of x to the natural log of 3. Because remember, power to a power, you would just multiply the exponent. So either way, it's going to be the same thing. And then e to the natural log of x is x natural log 3. And that's going to be easier to integrate. It is sneaky. That may or may not show up on your homework. So, we're going to rewrite this And it's also in the denominator, so I'm going to make the exponent negative and just say x to the negative natural log of 3 dx. So it looks like I made a big jump there, but if you look at the green, it makes sense. Any questions how I got there? Because now I can just use basic power rule for integrals. Add 1 to the exponent, divide by the exponent. So that is equal to the limit as a approaches infinity of... So if I add 1 to the exponent, it becomes 1 minus natural log 3. Divide by the exponent. And we're going to evaluate from 1 to a. And then I'm just going to plug in the limits and take the limit and see. Plug in the limits and take the limit. Seems like a sentence shouldn't make sense, but it does. So a to the 1 minus natural log 3 over 1 minus natural log 3 minus... And if x is 1, the whole numerator is just going to be 1 over 1 minus natural log 3. Let you chew on that. Make sure we're okay there before we take the limit. Yes, Karen.
I'm a little bit confused with how you got x to the negative natural log 3.
Well, so the denominator turned into this, but because it was in the denominator. Any other questions? Okay. What do you think? I mean, the only place that a showed up is right here, so what is this numerator approaching as a approaches infinity? Can you see it? Not going to be infinity. Because what's the value of the exponent? Is it positive or negative? Yeah. So infinity to a negative is going to put the infinity in the denominator, which then actually makes it go to 0. So this term goes to 0, and you're just left with the second term. So does that mean the integral converges or diverges? Yes. And if the integral converges, what happens to the series? It also converges. Now we just need to state that. So the summation of 1 over, what was it? 3 to the natural log of n, as n goes from 1 to infinity, converges by the integral test. Dun, dun, dun. Pew, pew. And there it is. That is how you use the integral test. Any questions? I know, right? Exciting stuff. Does anybody still need this? Because I'm going to give you one to try on your own. It'll be much more straightforward. Basically, I wanted to do this one with you because this sneaky trick does show up on your homework. Try this one. So this series, 1 over n, is called the Harmonic Series. You can call it by name. We can be friends with it. Hey, Harmonic, how you doing? Anyway, see if it converges or diverges using the integral test. Oops, wrong button. Yes. All right, here we go. So this one's very easy to show that the function's decreasing because the derivative is very straightforward. So we do know that the function is positive, decreasing, and continuous. And so the integral test is going to apply. And then actually working it out is straightforward. And yes, you'd have to show all of this work. The only thing that you may not have to show is, like on the test when we take it, I might have problems that say you don't have to prove the conditions are met, but you have to state the conditions are met. So like on this one, it'd be easy enough to look at 1 over x. Yeah, that's always positive, and it's always going to be decreasing, and it's going to be continuous if x is greater than or equal to 1. Okay. You just have to write those words, though. You don't actually have to find the derivative and show it. But other than that, you'd have to, for your work to be complete, you'd have to show all of this. So, yes, we have words. Haha. But anyway, that's it. And the Harmonic Series is actually a well-known series that is well-known that it diverges. So the good news is, if you have the Harmonic Series, now that we've done it once together, you don't have to do this again. You can just say, oh yeah, that's the Harmonic Series, it diverges. And that's good enough. Yay. All right, any questions about that? Yes.
Can you say about the A/B test?
Yes. Yeah, I don't know if you heard that question. It's a good one. Can you say that on the AP test? And the answer is yes. All right. Anybody still need this? Okay, the next thing you don't have to write down, but let's just think about this here. This is called the P-series. We looked at P integrals before. This is the P-series. And actually, let's just jump down to here. Oh, shoot. I don't have... Oh, man. I thought I left it there. Anyway, I'm going to just leave this. If we have time or whatever, or before the notes, before I post the notes, I didn't mean to erase this part. I had it all worked out. I'm just going to jump here. So it does turn out with the P-series that the P-series does sometimes converge, sometimes diverge. It depends on the value of P. And so if P is greater than 1, that series will converge. For all other values of P, though, it's going to diverge. And you can use the integral test to prove it. You can look at the integral test, and as you work it out, then you can play around with the value of P and show that it actually, that those conditions will make it converge or diverge. But just remember, if P is greater than 1, the series will converge by the P-series test. If P is less than or equal to 1, it will diverge. This is a really nice test when you can use it. It's very simple, though. Oftentimes our problems are not just this simple. But what we often use is the P-series in conjunction with other stuff. So I will give you guys the most complicated problem. Let's see, I'll freeze that while you guys are writing that. I have one. Whoop. Then I'm going to move up. Anybody still need that? Actually, I'll just leave it. We can have it on the screen. All right, so let's consider this. So first of all, look at that. Is that a P-series? Is it 1 over n to the power of something? It's a P-series.
Yes.
What is the value of P? So we're going to say it's a P-series with P equal to pi. What do you think? Why does it converge? Okay, let's say that then. So pi is greater than 1. And so, yeah. Does the series converge or diverge? And that's it, we're done. The summation as n goes from 1 to infinity of 1 over n to the pi converges by the P-series test. If only the AP tests had just P-series tests on them. You want to know something that's kind of a bummer for you guys?
No, not really.
The year that we went into closure, March of 2020. So, remember, I don't know if you remember, we had that long 4-day weekend and we just never came back from. That Tuesday that we were going to come back, that was supposed to be when my Calc BC class took the test on this. They never had to take that test. And then, that was, I don't know how many of you guys were taking AP tests that year, but the College Board actually eliminated a lot of material from a lot of the AP exams. They didn't eliminate all of this chapter, but they eliminated all the hard stuff. So, yeah, that year's AP class left out. They had to sit through all the torture of learning infinite series, but they never actually had to test on it. But not you guys. Sorry.
That's a good joke.
I know, right? Okay. Let's look at the comparison test now. We have 2 more tests. So the comparison test. Now we've kind of looked at the comparison test before in other, when we were doing integrals, improper integrals. But if you have 2 positive series, and you know one is always bigger than the other, if the bigger series converges, it's going to force everything below it to also converge. So if the bigger series converges, then the smaller series is also going to converge. And then if the smaller series diverges, it's going to force everything bigger than it to diverge. Oh, wait a minute. Oh my God, that's supposed to say diverge right there. Hopefully you didn't get to that last word. Also diverges. So your inequality's got to be going the right way. If we know that the smaller series converges, it tells us absolutely nothing about the bigger series. Or if the bigger series diverges, doesn't tell us anything about the smaller one. So, let's see how we can use this. Any questions about this one, though? Yes? Say it again? Mm-hmm. That's exactly it. What? It's kind of like the squeeze theorem. It's the same kind of idea, yeah. So oftentimes we don't have just the p-series by itself, because that's just so simple. But oftentimes what we do is we will compare other series to p-series because they're so easy to work with. So let's just take a gander here. Let's look at this problem. So one thing, just kind of food for thought, when you're trying to figure out what series to use, like I said, it's not really the focus for today, but we know about the integral test. What do you think? Is that argument easy to integrate? Yeah, we're probably not going to want to use the integral test on this. So what else can we use? Well, right now we know the comparison test, so let's give that a go. And I do see 1 over square root of n kind of hidden in there. That's like 1 over n to the 1/2. That's p-series. So let's try this. So if n is greater than or equal to 1, we know that the square root of n will be less than or equal to the square root of n times 3 to the n. So if I flip it, then 1 over root n is going to be greater than or equal to 1 over the square root of n times 3 to the n. And they're also greater than or equal to 0. So I've established my inequality here. So any questions just on that? Yeah, so I think you're seeing it, Kim. Yeah. So we can do the p-series test on the bigger one. Just think about it right now without writing it out. If we did the p-series test on that, is that going to converge or diverge? It diverges, and if the bigger series diverges, then what happens to the smaller series? Oh, man. So, sometimes this happens. The whole point of this, I mean, we are going to finish this problem. I'll show you how to do it. We have the skills. But sometimes, because, sometimes, like when teachers are just doing it. We always get it right. It's like, how do you always know? And the point is, you don't always know what to compare it to. You got to think, and then like, oh well, that one doesn't work. Let me try another one. Anyway, let's write this down though. Poop. The summation of 1 over the square root of n diverges by the p-series. It says poop. So that doesn't help us. So we try again. So let's try again. Another thing we could do is we actually have a geometric series kind of hidden in there. That 1 over 3 to the n. So let's see if the inequalities are going to go the right way on this. So I'm going to start with 3 to the n is less than or equal to the square root of n times 3 to the n. And then I can flip them. Remember, when you do the reciprocal, flip the inequality. And these guys are also greater than or equal to 0, so they're positive. Okay, that's a geometric, that would make a geometric series. Which, would that converge or diverge? That would converge. And if the bigger series converges, do we know something about the smaller one?
Yeah.
Oh, we found it. Okay. Now, the idea is like on a test, you wouldn't necessarily have to write this out. Sometimes it helps to just kind of sketch it out as kind of scratch work to get your head around it. But this is all just kind of scratch work, thinking about it. But we finally figured out how we're going to do it. So now we're going to do it. So does this, all this thought process make sense before we put down the final thing? Yes, it.
So why are we saying that this specific case is like somehow going to help us, and like the other one doesn't? The other one, like, it happens to diverge in the P-series test. But what if it's like it didn't diverge?
Well, if the bigger series converged, we could be done. We'd know which way to use to write our answer.
But for the second one, do we like already know that it's going to work? Is that what you're saying? Or
Well, I mean, it theoretically, what could happen is maybe you try comparing to one series, but it's inconclusive. You try another one, it's still inconclusive. You try another one, still inconclusive. Maybe it takes several tries before you finally figure out what to compare it to. This one, there's really only 2 obvious choices, but you just never know. So, all right, so our main work then will just simply look like this. Main work. So I'm going to state this inequality again. 1 over 3 to the n is greater than or equal to 1 over the square root of n 3 to the n, which is also greater than or equal to 0. We've established our inequality. The bigger series is a convergent geometric series. Because r is equal to 1/3. So, the series we're talking about, 1 over the square root of n times 3 to the n, converges by the comparison test. Dun, dun, dun. Yes.
For the comparison test, do you have to pick a function that, or a series that is included in the problem, or could you arbitrarily pick like a series like the harmonic series?
If you can establish the inequality, you can compare it to any series you want.
Okay, so you could just like say if you find any series and you prove that that series is going to be greater than the harmonic series, you can just say it converges. But
Yep. All right. So there's the comparison test. Any questions there? Okay. So here's our last test. The limit comparison test. So I'll let you write that down. And I do have a proof for this. I don't take the time to write the proof down. We'll walk through the proof real quick. Meant to have the proof still on there for the P-series and accidentally erased it. You'll actually find when we start really getting into this series, the comparison test is good. We often use the limit comparison test instead of the comparison test because usually the limit comparison test is just easier. You're going to see when we actually do it, and you can see it in here. We don't have to have an inequality going a certain way. That's good news. So the limit comparison, oh, Joshua, did you have a question?
Yeah. What were the squiggly things around A of n and B of n?
So if without the squiggly things, the A sub n just basically refers to an element. And then with the squigglies, now we're talking the sequence of all the elements. What was I going to say? Oh, so the basic gist of the limit comparison test is, so you're given one series. You find another series to compare it to, and I'll give you a hint of something that often works in a second. Just find another series, and then basically if the limit of the ratio exists, they either both converge or both diverge. So it's nice and easy. Yes?
So if you're trying to find something that converges, you always want to take another series that converges.
Well, I mean, the series that you're given either converges or diverges. So it's not like you want it to converge. You just want to figure out if it converges. So. All right. Anybody still need this before I please just kind of quickly go through the proof? Okay. When I say it can be used, it's good to use with these messy algebraic series. What I'm talking about there is, algebraic in general just kind of means, think about the basic operations, adding, subtracting, multiplying, and dividing. Now, exponents count in that because exponents are just repeated multiplication. Fractions count because that's just division. Square roots actually count in this case too. So if you have something that's just kind of made up of all that stuff, no sine, no cosine, no natural log, none of that, often the limit comparison test is an easy one, and I'll show you with our example, our last example. But before that, let me just kind of show you how this works. So if we look at this right here, I'll actually just use this. So these are just the conditions for using the limit comparison test. So you have to have a sub n and b sub n being positive, and this limit has to exist. So assuming all of this is true, then remember, if a sub n and b sub n are positive, then of course the ratio of those is going to be positive. And if the limit of these is L, then the ratio of these has to be less than L plus 1. Just go with the L plus 1. And what I'm saying right here for n greater than or equal to the little n greater than or equal to n, sorry, excuse me, it just means eventually that this can work. And actually this goes back to, I should have brought this up before I forgot. So we were looking at all of our series that we've been looking at so far, n starts at 1. But what if the n doesn't really start, or what if you're doing the integral test, for instance? N starts at 1, but for whatever reason, you cannot get the integral test to converge until n starts at, or the lower limit starts at 10. It's good enough, because if you think about it, if that integral will converge when your lower limit is 10, then we're saying that the series converges when n starts at 10. So if it already converges for 10 and up, it'll converge for starting at 1 and up, because that just adds 9 finite terms to it. So it's still going to converge. So this part over here is just kind of saying that idea, that eventually it works. So if I start with this inequality, and then I multiply through by b sub n, I get this inequality. And then it's kind of like the comparison test. So if a sub n, if the smaller series diverges, then the bigger series has to diverge. And if the bigger series converges, then the smaller series has to converge. And if we look at it the other way then, let's take the ratio going the other way, then the limit also gets flipped, but we basically do the same exact thing, and now if B, because this one had A sub n diverging, now we have B sub n diverging. So the whole reason for the flipping, so we could get it the other way. So either both of them diverge, or both of them converge. And that's kind of the gist of the limit comparison test, why it works. So this will get posted. If you want to chew on that, you can. I don't want to dwell on that. Let's just look at how we apply it. But any basic questions on this right now before I move on? Okay, our last example then is determine the convergence of that. And that's what I mean by a messy algebraic series. Don't worry, you're going to see that this is actually quite lovely. Yes. Yes, quite lovely indeed. I'll let you write down that lovely thing, though. So to do the limit comparison test, we're going to look at, we have to identify what our A sub n and our B sub n are. So let's let A sub n be that argument, n squared plus the square root of n plus 4 over 3n to the 4th minus n minus 1. And B sub n equals. So let's figure out what B sub n is going to be. What are we going to compare it to? Anybody have an idea before we give it away? I'll give you a hint. It's a P series. Anybody have an idea what P series we're going to use? Adon, did you want to try?
1 over n squared.
Yeah. Why'd you pick 1 over n squared?
We're going to follow like a limit, and then n squared over n to the 4th is 1 over n squared.
Yeah. Yes, Kieran.
So are we just trying to get similar degree polynomials?
Yep. Yeah, so if you basically look at the degree of the entire thing, so if you're not seeing that yet, and if you don't see it now, you'll see it when we actually work it out, but the numerator of this has a degree 2, and the denominator has a degree 4, which is kind of like if it simplifies, then it's like 1 over degree 2. So 1 over n squared. Let's do that. Because you'll see then that as we do the limit as n approaches infinity of A sub n over B sub n is the limit. Rather than putting a fraction over a fraction, I'm going to multiply by the reciprocal. So n squared plus the square root of n plus 4 over 3n to the 4th minus n minus 1 times the reciprocal of B sub n, n squared over 1. And now you can see that by choosing n squared, we have created the same degree on the top and the bottom. How nice is that? So the limit as n approaches infinity of n to the 4th plus n squared root n plus 4n squared over 3n to the 4th minus n minus 1. And what does this limit equal? Or does it exist? It equals 1/3. So the limit exists. So now we know that the limit exists. So what do you think? Does our original series converge or diverge? Yeah. Now here's what we have to do though. We still have to state that the summation of B sub n converges. We haven't ever said that. So I'm going to say the summation of 1 over n squared as n goes from 1 to infinity converges by the P-series test. So we can finally say that the given series, summation of n squared plus root n plus 4 over 3n to the 4th minus n minus 1, converges by the limit comparison test. There you go. So you can see the P-series we don't usually just use by itself. We usually use it when we're using it as a comparison for other tests. It's just easy. So there you go. 10.3 in a nutshell. Any questions about that?